In this video, we'll talk about situations where we have constant acceleration. The acceleration graph here has a constant value. This then leads to a linear velocity. If the acceleration is positive, then the velocity is an upward sloping line. If the acceleration is negative, then the velocity would be a downward sloping line. The position graph is then a parabola. If the acceleration is positive, then this is an upward opening parabola. If the acceleration is negative, then it would be a downward opening parabola. So in this case, we have positive acceleration, linear velocity, and parabolic position. Now, to look at this in more detail, we want to first go from position to velocity to acceleration. And the way we do that is that we remember our very fundamental that the average velocity equals delta x over delta t. And over this time interval here, we have a delta x that is this wide. I'm sorry, delta t that's that wide. We have a delta x that is this wide. So this means that the velocity is the slope of the position graph, just like it was in the previous video. And if I was to take and apply this formula to this complete interval, then I would get a line that starts at here and goes to there, and the slope of that line would be my average velocity. However, the object is actually not usually at that velocity, it's at a different velocity. And if we take the equation here and we take the limit as delta t gets smaller and smaller to 0, then the velocity, instantaneous velocity, is equal to the derivative of the position function. The derivative is a calculus method of taking the slope of a curve. So in this case, our curve is a parabola. What does the slope of a curve mean? Well, the slope of a curve at any point means the slope of the tangent to that curve at that point. And so we can see that initially the tangent line is very shallow and gets steeper and steeper and steeper. And so that corresponds to a shallow line here corresponds to 0 here. As we get steeper, we get increasing slope on the tangent lines, and we see that the velocity curve just keeps getting steeper and steeper and steeper. We could do the same thing again and say that the acceleration equals the change in velocity over change in time. That's average, which in this case it's a constant velocity, so that's true. In cases where it's maybe not constant velocity, then we can take the limit as delta t goes to 0, and then we have the acceleration equals dv dt, the derivative of the velocity with respect to time, and that gives us the slope of the velocity. So in generating the velocity graph from the position graph, I take the slope, and then I do it again to get the acceleration. Going back the other way, we do the integral, and that's the area under the curve. So this area under the curve is how far our velocity changed, how much our velocity changed, delta v, over that period of time. So delta v equals a delta t, or if we're looking at this over a curve, then we integrate, so the change in velocity equals the integral from t1 to t2 of a dt. That will map this area under the acceleration curve up into the velocity. So we do this again. Delta A, delta X is now my V delta T, and that gives me the displacement as I take the limit as delta T goes to 0. And I can do integration where my displacement equals the integral from time 1 to time f to tf, ti to tf of v dt. So the goal here is that you should be able to go from position graph to velocity graph to acceleration graph and backwards. So if I have a acceleration graph, then I can take the area under it and find the velocity graph, take the area under that, and find the position graph.